Okay, we are still in chapter 3. We're still talking about differentiation. And you've just finished exam 1. Congratulations. I'm really hoping everybody did well. And now we're moving into section 3.3, where we get into what are called differentiation rules. So what's going on here is that you've now studied for a long time limits, and then the concept of a derivative, which gives us the slope of the tangent line to a curve at any point, and how the derivative of a function f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And you have to do some algebra and simplify and then take the limit by plugging in h equals 0. So now what's going on is that's like a really hard way to take the derivative. So I'm sure you would agree with that, and I'm also sure that you would like to know that, hey, there's some rules. So what's happened is mathematicians have proven that for certain types of functions, the derivative will always be a certain thing. So the first one is the derivative of a constant. Like if I have f of x equals a constant. Now f of x equals a constant is a straight line that looks like this. And so even just understanding the derivative is the slope of the tangent line to this curve. Well, the slope of that is always 0. So the derivative of any constant, no matter what that constant is 0. Okay, that's called the constant rule. Then we have the power rule, and this is the general version, and I'm not going to prove this to you because I would have to use what's called the binomial theorem, and I don't really want to get into that too much. But in the power rule, what I want you to remember is if you have the derivative of x to a power, okay, and it's any power, n is any power except for, no, it's any power, the derivative of x to any power, okay? The way it works is that you take the power, you bring it down in front, and then you subtract 1 from the exponent. So the derivative of x to any power n is n times x to the n minus 1. So let's see how this works with several examples here in example 29. So in part A, we have y equals x squared. We want to find the derivative with respect to x, the derivative of y with respect to x. Okay, so from the power rule, we know we bring the 2 down, put it in front, subtract 1 from the exponent, so we have 2x to the 2 minus 1. So if I simplify that, it's simply 2x. Y equals x to the 2/3. How does that work? Again, bring the exponent down in front, which makes 2/3 x to the 2/3 minus 1. 2/3 x to the 2/3 minus 1. 2/3 minus 1 is minus 1/3, so it's 2/3 x to the minus 1/3. If you want to, that's a negative exponent, so you can put it in the denominator as a positive exponent. So that's 2 divided by 3x to the 1/3, and then x to a fractional power like that we know is a root, so that's the cube root of x. So it's 2 over 3 times the cube root of x. As we move on later, a lot of times this form of the answer is going to be fine, but I kind of want you to see that when you simplify it, it looks something like this. We start off with x to the 2/3. The answer is, the derivative of that is 2 over 3 x to the 1/3, or the cube root of x. What if I have x to the square root of 2? There's really nothing more I can do than this one other than bring the square root of 2 down. When I want to take this derivative, bring the square root of 2 down, and then subtract 1 from that, x to the square root of 2 minus 1. I can't simplify this anymore unless I were to write square root of 2 as a decimal, but then it's no longer exact, right? 1.414 forever, non-repeating. Even if you did that, you'd write a few decimal points. It's not exact anymore, so we just leave it like this. In part D of example 29, y equals 1 over x to the 4th. So I need to write that as x to a power first. So 1 over x to the 4th is the same as x to the minus 4, right? Positive exponent in the denominator is a negative exponent in the numerator. Once I have it as x to a power, then the derivative, I follow the same rule. Bring the negative 4 down, and then subtract 1 from the exponent. So minus 4 minus 1 is now minus 5. So it's minus 4 x to the minus 5. If I want to put that back into the denominator as a positive exponent, it's minus 4 over x to the 5th. Y equals x to the minus 4/3. It's the same idea. If I want the derivative of that function, bring that power down, so it's minus 4/3 x to the, subtract 1 from the exponent, so minus 4/3 minus 1. So that's minus 4/3 x to the minus 7/3. Again, if you wanted to put that in the denominator as positive x to the 7/3, you could. I mean, x to the positive 7/3, you could. But we'll just leave it like that. X to the square root of 2 plus pi. Okay, so what I could do is just bring the square root of 2 plus pi down, etc. But notice that x to the square root of 2 plus pi is the same as x to the 2 plus pi to the 1/2. So that's when I distribute the 1/2 through, that's the same thing as x to the 1 plus pi over 2. So the derivative of that is bring that power down, 1 plus pi over 2, x to the 1 plus pi over 2 minus 1. So that's 1 plus pi over 2 times x to the pi over 2. So then I'm factoring a 1/2 out of that, 1/2 times 2 plus pi, right? Distribute that to give me 1 plus pi over 2. X to the pi over 2 is x to the pi to the 1/2, so that's the square root of x to the pi. This simplification is not necessarily, you don't need to go that far. I just think it's interesting to see it in a form that looks a little bit more simplified to us and complete when we're working a problem. And that's the end of example 29.